Okay, so here we have an example. So it says decompose the given rational expression with distinct linear factors. What they mean by distinct is that factor is not the same as that factor. And they're both linear, meaning that the variable has a degree of 1, or the factor, I should say, has a degree of 1, right? Now, if you're thinking, well, wait a minute, I could multiply that out and then I'd have x squared. True, but we're looking at factors, okay? All right, so there you go. I'm going to recopy it. This is so exciting, our first one. And what I'm going to do is I'm going to say that's equal to something plus something. And first I take care of the denominator. So what I'm going to do is I'm going to split up those linear factors. So x plus 2 for that one. You can put it in parentheses if you want. It doesn't really matter. And then the other one's going to be x minus 1. Okay? Now, you can say, well, that's great, but what about the numerators? And you might be thinking, oh, 3x, maybe it's 1x and 2x, or, maybe. But we don't know what it is. What we do know is the linear factors have to be a degree less than 1. So when you have a degree less than 1, that's a constant. So I'm going to use A for that constant, and I'm going to use B for that constant. Now you might say, yeah, but in your example you used a sub 1 and a sub 2. You can do that if you want to. I think it's just easier not to deal with the subscripts. And I don't think we're going to have more than 26 linear factors. There's 26 letters in the alphabet, so I think we're okay. And I've always seen it done this way. But, okay, so now we have to find A and B, basically, is what we're trying to do now. What we're going to do is go through that process then of finding the common denominator. So it's going to look like A times x minus 1. This is how we would add them, right? And then over here it'd be B times x plus 2. Right? And then you would get in the numerator I'm going to go ahead and multiply it out. Well, it's our first one. I'll write it. Ax minus 1 plus b times x plus 2 all over that common denominator x plus 2 times x minus 1. Okay? So now what we're trying to do, we've got the denominator, right? That looks like x plus 2, x minus 1. That looks like x plus 2, x minus 1. So now what we're going to say is 3x has to equal a times x minus 1, oops, x minus 1, plus b times x plus 2. Okay, and so we don't really have to worry about the denominators now. We got the denominators the same. What we're doing is we're setting the numerators equal to each other. And you might be wondering, okay, well, how's this going to work out, And usually we don't do quite this much writing, but it's okay. I wanted to show it to you in all its steps. So I'm going to distribute, and I get ax minus a, and I'm going to distribute, and I get bx plus 2b. Okay, now here comes the exciting part. Well, it's all exciting, but see, this is a 3x. That means that ax plus bx has to equal 3x. So what I'm doing is I'm saying the x terms on the right have to add up to the x terms on the left. Well, there'll only be one x term on the left, but that's what it has to be. Now, you could say, well, that's good, that's cool. And you might even realize, okay, well, they all have an x, right? So I can say 3 has to equal a plus b. And you're right, okay? That's a lovely equation. We don't know what a and b are. Could be 1 and 2, could be negative 2 and 5. We don't know, okay? But we have another equation. Our other equation, let's see, I'll write it in green. I have no constant over here. 0 is equal to negative a plus 2b. So the constants on here were negative a and 2b. Now, you might be saying, well, how do I know those are constants? They look like variables to me, Mrs. Christensen. Well, a and b are, we don't know what a and b are, but they're not the variable x. They're representing real numbers, okay? So whatever the real numbers add up to, it has to add up to 0, which is the constant on the left-hand side, because there's no like +5 or -7 or something like that. If there were, then it would equal -7 or +5 or whatever. But it's like +0 here, okay? All right, now we're getting somewhere. So if you look at this equation and add a to both sides, you get a equals 2b. And now you can use these two equations together. It forms a system of equations. And I'm going to use substitution because it'll be easiest. 2b, and I'm going to plug that in for a. So I'm taking the 2b and I'm putting it in right there. And then that gives me 3 equals 3b, or b equals 1. Right? Divide both sides by 3. Okay, so now what is a? Well, I can go back and substitute this in. A is going to equal 2 times 1. This one isn't very exciting. It really was 1 and 2. Okay, now what matters though is how we write our final answer. And by the way, these do take some paper sometimes. Okay, so go way back to the original thing that we had. We had this part. I'm going to skip over that orange stuff. And that, okay? So we had a over x plus 2 plus b over x minus 1. That was our setup, right? But now we know what a and b are. So, well, you can't see it anymore. Let's see if I can squeeze it in here. What did we say a was? 2. So 2 over x plus 2 plus, and b was 1, right? 1 over x minus 1. That is the partial fraction decomposition, okay? Now, you might be like, wow, that's really cool. Or you might be like, I don't believe you. I don't think that works. Okay, so remember what you're trying to get. 3x over that denominator. Okay, let's check it, see if it works. This will be the long video. Okay, if I got common denominators, then in the numerator, I would get 2x minus 2 plus x plus 2 all over that common denominator. And then the 2's would cancel. 2x and x would be 3x. Yep, it really worked. So I love a good partial fraction decomposition problem. That's the check. The answer is up here, my box here, which is now a circle. Okay.